doesn't have a contiguous pi system, plus it's puckered, it's not planar. So this is not aromatic, and we're done. But there are compounds that pass the first three tests. And so those compounds are either aromatic or anti-aromatic. If they pass the first three tests, one of two things will be true. Either they will have 4n plus 2 pi electrons, or they'll have 4n. If they have 4n plus 2, they're aromatic. That is almost all of these things we looked at, except for this one. If, on the other hand, they have all of these three, and they've got 4n, they're said to be anti-aromatic. Anti-aromatic compounds are as unstable as aromatic compounds are stable. So while compounds will bend over themselves to become aromatic, they will avoid anti-aromaticity like the plague. And I'll give you a nice simple example. It turns out, just to give you an illustration, if I started off with, yeah, that's good. If I start off with this compound, what I find is that if I compare it to, say, this compound, I find that this H is about 100 million times more acidic than this H. I can measure the pKa values. This is 100 times more acidic than this one. And why the heck would that be? Because if I pull off this H, right, if a base comes in and pulls off that proton, what I will get will be a species where the negative charge is resonance stabilized. So it has some acidity. Well, why is that one so much more acidic? And the answer is, if a base comes in and pulls off this proton, what I end up getting is not just resonance stabilized, it's aromatic. And aromaticity is a major driving force, it's a major stabilization factor. So this species is going to fall over itself to lose that proton. Okay, if I have this compound, I'm going to take this off. If I have this species, so let's pick a really good leaving group, like say iodide or maybe maybe a triflate. So triflate is the world's best leaving group, right? So if I take this compound, so you remember from your organic 1, really quite frankly, if I take this compound, this compound in a polar solvent like DMSO, this is going to ionize to give you the carbocation, right? That's going to ionize in a flash to give rise to the carbocation, even though the carbocation is secondary. The rate at which this one will ionize is going to be, I don't know, 1 million times faster because the carbocation here, right, is going to be resonance stabilized. So this process is going to happen much faster because of resonance stabilization. So I might expect, geez, if I put another double bond in, it should even further stabilize the carbocation. So the rate at which this one will ionize should be millions of times faster than this one. Here's the kicker. This will not ionize. Even with the world's best leaving group and the presence of 2 double bonds, this will not ionize because if it did, it'll give rise to that species. And this is cyclic, planar, it's got a contiguous pi system, but it has 4n pi electrons, right? Well, in this case, you know, right, so it's got four electrons, right? 2, 4. So this is when 4n, when n is equal to 1. That is anti-aromatic. And as much as things will bend over backwards to become aromatic, they will fight tooth and nail to avoid becoming anti-aromatic. So this species is so unstable, even with the world's best leaving group, it does not form. Okay? Okay, so we'll stop there and then we'll continue the lectures on reactions or ionic compounds. Thank you.